without further ado, I'm going to hand over to Sven, who's going to talk to us about reading the fossil otolith record. So over to you, Sven. Thank you.
Yeah, thanks, Adrian, for the nice introduction. So I'm doing currently my postdoc at the Smithsonian Tropical Research Institute in Panama, but I will mainly talk about my research, which I've done back in Barcelona at ICTA, as like the last chapter of my PhD. And the research here, but also there, was mainly centered about like this tiny guy, a lanternfish, which is a fish, not bigger than the size of the little finger, but quite an important fish as it is an indicator for like mesopelagic ecosystem health, because it comprises more than 200 species. It is globally distributed from polar to tropical waters, occupying like several depth niches, and makes up 65 to 75% of mesopelagic fish biomass. And this is crucial since like mesopelagic fish biomass is estimated to be bigger than 10 times the annual world fishery and aquaculture production, right? So this makes the fish a key player in the marine food web, as it transfers energy from lower trophic levels to higher trophic levels, and also is like a key prey for apex predators like tunas, sharks, marine mammals like whales and dolphins, and even seabirds. But at the same time, it is also very important for climate regulation, as it goes like diel vertical migration. So during the day, it hides into in the deep sea and oxygen-deprived waters, and during the night, it swims up to the surface to feed on zooplankton. And this diel vertical migration sustains the carbon cycle. But those fish, even though it is adapted to low oxygen conditions, it might be under threat through one of the consequences of climate change and ocean warming, which is ocean deoxygenation. So I think you've seen like this map already in an earlier talk from Andreas Oschlies, which shows the change of oxygen in inventory in the upper 1,200 meters from a period from 1960 to 2010. And this observational data shows that in the last 50 years, the oxygen or the ocean has lost 2% of its oxygen. And this is most severe in the areas which are marked here in dark red. But beside like this phenomenon of like pure oxygen loss in the ocean, there is like another phenomenon or process going in parallel, which is the expansion and shallowing of oxygen minimum zones, right? So you have like those oxygen minimum zones, or the largest oxygen minimum zones in located in the eastern upwelling boundary systems, so in the Arabian Sea, the Eastern Atlantic, and the Eastern Tropical Pacific. And observational data, but also modeling data shows that in the last 50 years, but also projected in the next 100 years, those oxygen minimum zones, which mainly occur like around like 300 to 500 meters depth, they're expanding in volume and moving closer to the surface. And this is thought to have like significant impacts on pelagic ecosystems. So we see here a model from Seibold and Wishner. And this model shows that like an expansion of the oxygen minimum zones affect the marine organisms in two ways. So particularly the diel vertical migrators, they have to migrate longer or transit longer through oxygen deprived regions. And at the same time, organisms which live on the surface, they experience like an vertical aerobic habitat compression. So the habitat is becoming smaller, which in turn then changes like prey-predator relationships. So the predator pressure enhances or is thought to enhance. So what we know fairly well is like how like single marine organisms respond to like reduced oxygen levels, like with fish being the most sensitive groups to hypoxia. But what we don't know yet is like how like entire pelagic ecosystems might be affected by an expansion and a shallowing of oxygen minimum zones. As well, it is still unclear like how ocean deoxygenation interacts with other climate change stressors, like ocean warming, acidification, or productivity changes. And since we have just like monitoring and observational data for like the last years or decades, it is also unclear like how pelagic ecosystems respond on longer geological timescales to ocean deoxygenation. So the research question I've asked in my last study is like how mesopelagic fish communities respond to ocean deoxygenation, also like in parallel or along with other climate change stressors over timescales covering like centuries to millennia. And the approach I've used is a micropaleontological approach. So it is I look at like a geological natural experiment in the past to test the response of fish to deoxygenation. So why using that approach when we have like all this nice methods already to investigate like the mesopelagic zone? So for example, midwater trawls, which is like the best reliable method for physical species collection of large volumes. We have like this HUVs, RUVs, and AUVs, which is the perfect tool for in situ observations or like observing situational awareness, or like echo sounders, which are like the non-invasive, most efficient tool for biomass estimations, right? As well as Argo floats and CTD downcast, which is like the gold standard of measuring like the chemical and physical composition of the water column. But this methodological tools, they are coming with trade-offs. So for example, they might be expensive and complex. So for midwater trawls, we need like a big boat, like a powerful engine, and we have to do that several times throughout the year. So it becomes like expensive as well. RUVs, HUVs, AUVs can be also complex to handle, and there's always a mechanical risk. And I would say the biggest trade-off is that all those methods, they just provide like a snapshot in time, right? There is not observational data which goes over centuries to millennia. And with my research, I try to kind of fill this gap. So what I'm using is like fossil otoliths. Maybe you've heard from the talk of Qianzhen Lin. He also talked about like, or he also used a similar method for his research. So each fish has like 3 pairs of otoliths, right? The sagittae is like the most important one for fishery research. They are parts of the inner ear made of calcium carbonate. And when a fish dies, they sink down to the seabed and get accumulated over like centuries to millennia. So all that information, which is stored in this otoliths, gets preserved over very long time scales. And this information is, for example, if you look at the shape, so each otolith has like a species-specific shape, you can make assumptions about changes of the fish assemblage through time. The same for the otolith size, and the otolith increments give you information about like the fish size and growth rates in the fish. And you can even look at the geochemical signals using isotopes and trace elements to infer like metabolic rate changes or, for example, the exposure to deoxygenated conditions. So what I did, I then moved like to the Eastern Mediterranean, which is like the perfect setting for my natural experiment. So we collected a huge custom load core, which spans in area 30 times 30 centimeters, right? So it is like way bigger than like a gravity core or a multi-core. So it contains like a lot of sediment material. And the length of the core was around like 2.5 meters. After 14C dating, we knew that it spans almost the entire Holocene, so back to 10 to 11,000 years before present. Then the question was why we moved like into that area, and we moved to that area because it has like a special geological setting. So it contrasts like 2 very different environments through time. So I don't know if you see like the black layering on the left side of the core, which is marked here with a yellow box. Those are called like subropel layers. And they formed around like 9,000 to 6,000 years before past. And that's because the environmental conditions were completely different to the conditions we have today in the Mediterranean Sea. So at that moment, the climate was way more humid. We had like a lot of precipitation, and that precipitation flushed like a lot of nutrients into the Eastern Mediterranean basin, fueling the surface productivity. But at the same time, it also created like this freshwater lid on top of the basin, which enhanced the vertical stratification and therefore impeded the thermoinhalant circulation. So impeded like oxygen getting mixed into deeper zones in the Eastern Mediterranean. And the result was that we have like a highly productive system, like at the surface, but and also very anoxic conditions in mid to bottom waters. And those both conditions created like this black organic rich layers as like more surface productivity or more organic matter sink down to the seabed, and at the same time, this anoxic conditions impeded like decomposition. And if we look at the last 7,000 years, we have like a contrasting environmental setting, which is more similar to the environmental conditions which prevail nowadays in the Mediterranean Sea. So we have like a very arid climate, less precipitation, so less nutrients flushed into the basin, which causes like an ultra oligotrophic setting with a strong thermal circulation and therefore like a well oxygenated water column. So I have like this flip-flop systems, this contrasting conditions now, and now I wanted to see like how the otolith accumulation rates have changed throughout that times. So we sliced the core in centimeter slices and then just picked out the otolith with a mesh size bigger than 250 microns. And what we get is first that the overall otolith abundance is lower in the subpropel formation. So when we have like this anoxic conditions, and they're way higher in the last 7,000 years. And when we look also at like the relative fish composition during that time, we see that during the last 7,000 years, where we have like a well-oxygenated Eastern Mediterranean basin, the lanternfish, they dominate the record. They make up more than 80% throughout the last 7,000 years. While we look at the last 9 to 6,000 years, when we have highly anoxic conditions, the lanternfish become nearly absent in the record, and more epipelagic fish dominates the record, like European anchovy and the silvery lightfish, which is assumed to change their diavertical migration behaviors to more epipelagic schooling. So the interpretation from those results were that during times of a well-oxygenated basin, the lanternfish were doing quite well with high abundances and high biomasses, and it could undergo their diavertical migrations, while the epipelagic fish is in biomass lower, since we just don't have like the primary productivity to sustain them. And if we look like at the subpropel formation, where we have like this high anoxic conditions, so we have like an oxygen minimum zone which expands to the bottom and also to like depth of 100 to 80 meters below the sea surface. The lanternfish is doing quite bad, as it can't sustain the diavertical migration, even though adapted to low oxygen conditions. The oxygen conditions are like so low or so anoxic that it even harms the lanternfish when doing like their daytime habitat at depth. And at the same time, when they swim to the surface during the night, they experience like a compressed vertical habitat, which harms them again and diminishes their abundance of their biomass. And in comparison to that, we have like the epipelagic fish, which benefits from like this compressed vertical habitat zone, and also from the high nutrients and high productivity in that basin during that time. So the take-home messages from that study were that we can show through like a natural experiment contrasting responses to fish to deoxygenation. And if we spend it to the future, we might assume that under very anoxic conditions in a future ocean, the mesopelagic fish abundance reduces. While in contrast, epipelagic fish might cope better with a hypoxic ocean in the future. So this is what I've done in the Mediterranean when working like in Barcelona. But then the question was like, where going next, or where bring next like that research, and that brings me to yeah, the map I showed in the beginning. So we have here like the three largest oxygen minimum zones in the global ocean, right? And the largest oxygen minimum zone is in the yeah, tropical eastern Pacific, since it hosts over 95% of world's suboxic water volume. And when we look at observations and predictions, it has expanded and shallowed in the last 50 years, and it will so in the next 100 years. So I thought this is the perfect setting to continue like my research on surface otoliths. So let's just maybe talk quickly about like the environmental setting. So we have here also a very contrasting environmental setting in both basins. So in the tropical Eastern Pacific, this region is mainly characterized by strong seasonal upwelling. So from January to March, we have like the strong upwelling, which is reflected here in the average February sea surface temperature in blue. And this brings nutrients to the surface, fuels the surface productivity, and in turn as well, so, fuels like the oxygen minimum zone. And on the other side of the isthmus, we have the Caribbean Sea, which has no seasonality, no upwelling. It is an ultra-oligotrophic basin, and we have a well-oxygenated water column. So yeah, a very contrasting setting in the modern ocean. At the same time, this area is interesting and also interesting to work at STRI, because STRI holds a very large collection of geological samples, which is from like the PPP, the Panama Paleontological Project. So you can see here, well, this is samples which are collected since like the 80s, and they comprise surface sediment samples, which are collected by grab samples and dredge samples in blue, but also like fossil sites in Panama inland. So like the conditions couldn't be better to continue the research here. So jumping at the research question, which I wanted to look at in this setting, is how lanternfish energetics change along environmental or strong environmental gradients with respect to oxygen, productivity, and temperature. And the approach is similar to the approach which I used in my last study. So using like fossil to subfossil otoliths in surface sediment samples across the Isthmus of Panama and from fossil sites spanning the last 8 million years. So the methodology looked like follows. As I explained before, we have like this contrasting environmental condition in the modern ocean. So I collected surface sediment samples on either side, but I also went back in time. So 5 to 8 million years, when the Panamanian Isthmus wasn't closed at that time. And at that time, we just didn't have like warmer temperatures, but also higher productivity on the Caribbean side, as the gateway was open, and that caused like seasonal upwelling also on the Caribbean side. So what I did, I collected the samples, picked all otoliths, and identified the entire assemblage, but then focused on otolith length measurements. Because if you apply like family-based allometric power models, you can estimate from the otolith length the total fish length of the lanternfish. After obtaining the total length, I used published length-weight relationships to estimate like mean per capita fish biomass. And as a last step, multiplied like the mean per capita fish biomass of lanternfish with the relative abundance for each site or each time period. So I get a measure of like the relative abundance of lanternfish through time and across the Panamanian Isthmus. So the preliminary results for that look like that. These are the relative abundances of lanternfish in the otoliths assemblage. So you can see here in dark blue the modern Pacific, and in light blue the modern Caribbean. And the red box plots, they show the modern Caribbean fossil sites throughout the last 8 million years. So you can see that the modern Pacific is in lanternfish biomass high, or in lanternfish abundance, relative abundance higher than the modern Caribbean. Has the lowest values around like the closure of the isthmus. And then if you go back in time to the late Miocene, the relative abundances increase. The graph for the lanternfish sizes looks very different to that. So we have almost no changes in lanternfish size throughout the last 8 million years in the modern Caribbean. But what we can see is that we have anomalously small lanternfish in the modern Pacific. And this is a surprising result because if you look at other fish or other organisms, like benthic organisms across the isthmus, they tend to be bigger in the Pacific than in the modern Caribbean, which is mainly due to the high productivity regime in the modern Pacific. So we relate the small size of lanternfish first to the intense oxygen minimum zone. So living like in lower oxygen conditions decreases the growth rate, but at the same time we have like higher predation pressure as well, like in the modern Pacific, which might just decrease the size of lanternfish as well because they don't grow that old as they were preyed on before. And then as a last step, I said I estimated the relative biomass for those sites and through time. And here you could see in the modern Pacific and the modern Caribbean that the size and relative abundance differences from both sides, they balance each other out. So we have more or less the same biomass in the modern Pacific as in the modern Caribbean, or the same relative biomass. While when going back through time, the biomass increases to the late Miocene. So as a last slide, I don't know if I run out of time. As a last slide, is just the preliminary conclusion, what I got from my preliminary results. So we have the modern Caribbean, right, where there's a weak or almost no oxygen minimum zone. So we start from that kind of ocean system, and then we move to the modern Pacific, which could be seen as future ocean one, as we have like the same water temperatures, but a very expanded and shallow oxygen minimum zone and a high productivity surface layer. And so what happens is that the fish become smaller, but increase in relative abundances, and therefore the biomass stays the same. While if we go to another geological analog, the late Miocene, where we have a weak OMZ, but like higher temperatures, it seems that the lanternfish, they thrive in that condition. So they have the same sizes as in the modern Caribbean, but they increase significantly in abundance and therefore in biomass. So that was the work which I've done so far with lanternfish otoliths in the fossil record. So I want to thank first you for like your interest in my research and for the attendance. Then of course I want to thank like all my co-authors for the studies conducted so far in Barcelona and here at the Smithsonian. And then I want to show you that picture on the left as a call out for research cruises in the tropical Eastern Pacific. So as a Smithsonian, we don't have a research vessel here. This research vessel is from the Max Planck Institute in Germany, and this was located here for the last 3 years. They conducted a lot of great research, measuring like the physical and the chemical conditions in the ocean, and in particular between the Galapagos Islands and the Gulf of Panama. But a research vessel is missing, which could really be doing like the hard work, like geological sampling or even like midwater trawling. And since there aren't a lot of studies or any studies in that region about that, it would be highly needed to conduct research cruises here. So if anybody knows about planned research cruises or research cruises in organization, it would be great to just talk about it and talk about if anybody knows anything. So I want to close my talk with that last slide and then hopefully open to some questions.
Excellent. Thank you very much. We haven't had so many talks linking sort of the deeper time to the present, so it's nice to see that perspective. Hand it over to the people in the audience. If anybody's got any questions, please feel free to raise your hand or type something into the chat.
I'm not sure how to chat. How do I raise my hand?
Hi,
Uh,
Clive.
yeah, sorry, I was just failing to find how to raise my hand. Um, Brilliant. Thanks very much. That's awesome. I mean, I'm very interested in extracting energetics data from otoliths. And obviously, I think there's an enormous potential to get some additional individual energetics data from those otoliths, which would be fabulous to see. Um, I had a quick question about sort of the preservation and the taphonomy associated with those otolith collections. And can you be sure that the collection method, like the transfer method of the otolith to the sediment surface, is consistent across your comparisons? To what extent are they predator-derived otolith assemblages rather than, I mean, presumably most of them are predator-derived. So does it make any difference that the potential predators providing otoliths have also changed over that time period?
Yeah, that's a brilliant question, right? So the answer is we just don't know. But yeah, that has to be considered because the oldest assemblage in the surface sediments, they just don't reflect like what was in the water column above those surface sediment samples. Of course, it could be brought into that area by other predators, right? I just mentioned that predators in the beginning. They could just bring in that otoliths from other areas, and then it's more that it more reflects like yeah, a record of the predators than maybe of the lanternfish. But at the same time, we have like also, yeah, this otolith could also be brought out of that area, right? Through, for example, fish and also pelicans. So if we open the stomach content of pelicans, we find like, yeah, like heaps of lanternfish otolith in that. So yeah, this is a yeah, a big difficult question. So of course, this makes a difference in the Caribbean compared to the Pacific, right? Because we have so much more predation in the Pacific than in the Caribbean. So yeah, that has to be considered. But how to consider that in a yeah in a smart way needs still to be addressed.
Yeah,
Yeah.
yeah. Cool. Thanks.
Yeah, interesting. Yeah, it hadn't occurred to me at all actually, but yeah, fascinating. Thank you. Um, right, well, Sven, we should move on to the next talk. So thank you very much as an excellent talk, and also thank you for uh, the request for people who might have cruises. So hopefully anybody on the call, but also people watching on YouTube, hopefully will get in touch with you about something. But thank you once again for an excellent talk, and for anybody who might still have questions for Sven, then please do feel free to email him. I'm sure he'll be happy to answer them after the talk. Okay, thank you.